Welcome back. We're in Chapter 2, our chapter on logic. We're in Lesson 2, where we will be talking about definitions. This is a rather short lesson. You'll see a link here to logic outside the box. We probably will have covered that in class, as we will with these mind traps. There are several of them in a row. If this is your first time at it, why don't you pause at each one, think it through, and see if you can come up with the solution. I'm just going to zip through them here a little bit. Again, feel free to pause, think about it if you haven't already. These are going to actually be our quiz in class. Might take this opportunity, if you didn't do well in the quiz, to give these a try again. See if you can come up with the right answer. We're trying to practice with conditional statements here. And some of the other conditionals that we had: contrapositives, converse, inverse. All right, then, let's get going with the lesson. We have some symbolism that we need to be comfortable with as we work with our conditionals and our logic. What do you think that means? It's a way we would express a conditional statement. We would read this: if A is true, then B is true. Or if A, then B. Or we might say A implies B. All acceptable ways of reading that. This you could probably get then. B implies A, or if B is true, then A is true. And how is that actually related to this first sentence, or first statement? Hopefully you've got that one. That's correct. It's the converse of it. We interchange the hypothesis and the conclusion. We'd read this: if not A, then not B. Or not A implies not B. How is this statement related to the original one? You're right. Yes, you can see that it's not in front of each, so it negates them. That makes it the inverse. Kind of interesting question. How is this one related to the converse? B implies A, not A implies not B. Interesting. This is actually the contrapositive of the converse, but it's the inverse of the original. Kind of makes sense, because we learned that a statement and its contrapositive are logically equivalent. The converse and the inverse, we learned, are logically equivalent. If B is not true, then A is not true. Or not A implies not B. Or if not B, then not A. And of course, this is the contrapositive. Going to look at some Euler diagrams. If A is true, then B has to be true. If A, then B. There's another conditional that would fit. You know what it would be? Think about it. Make a guess at it. Did you come up with if not B, then not A? If not B, it would have to be way up here. And if it's not B, there's no way it could be in the A. We say that's logical equivalence of the original and its contrapositive. Now we have if B is true, then A is true. You got the picture figure out, the Euler diagram? Sure, if B is true, then A is true. So if we have a statement that's true there in the hypothesis, then A has to be true, because all of B is inside of A. If not A, then not B. Again, you can see this is the contrapositive of the original. And the same diagram is going to work, because if it's not in the A circle, it can't possibly be in the B circle. So once again, we have logical equivalence. I mentioned earlier that this lesson is about a definition, and what makes a statement a good definition? When you think about definitions, you think about it. It's a statement that tells what the word means. Well, in geometry, we're going to define it a little bit differently. We're going to say when both the original conditional statement and its converse are logically equivalent, mean the same thing, then the original statement is a definition. What's different about this? We've been saying the original statement and its contrapositive are always logically equivalent, and that's true. But if we find out the original statement and its converse are logically equivalent, then that original statement is a really good definition. I do ask this question, what's probably also true of the inverse and the contrapositive? Correct. They are all logically equivalent. They all mean the same thing. Here's a good example. If three lines are concurrent, then they intersect at the same point. So if three lines are concurrent, they intersect at the same point. The hypothesis is here. If three lines are concurrent, then they intersect at the same point as the conclusion. What would be the converse of this? Pause it and give yourself a chance. Converse, you just interchange. So if three lines intersect at the same point, notice I brought the three lines in here just so that it read better, but we've got intersect at the same point. So if three lines intersect at the same point, then the lines are concurrent. If they intersect at that point, then they're concurrent. Is that true? It is. Are the conditional statement and its converse both true? Yes. Then the statement is a good definition. So this statement would be a good definition of the word concurrent. Matter of fact, it's one that you should have memorized by now. So there's a definition because it's conditional and the converse are logically equivalent. So some symbolism of definitions. So if A implies B and B implies A, so the original statement and the converse, well, then what must be true? Well, we say, then, well, this is how we write it, then A implies B and B implies A. We read it a little differently, though. We say A is true if and only if B is true. It's abbreviated like this. A, if and only if B is true. Anytime you see these three letters together like this, you know that that statement is a definition because A implies B and B implies A. So A is true if and only if B is true. So that's our lesson. So we're right into the questions already. So we're looking at this statement, all geese have two legs. Is that a good definition? Thinking about that a bit? What would make it a good definition if its converse were true? So he's going to walk you through that. Write the statement in if-then form. Illustrate it with an Euler diagram. Write the converse of the statement. If we assume the original statement is true, does it follow the converse is necessarily true? Original and converse. Okay, another statement. If you are an astronaut, you are not more than 6 feet tall. Is that a good definition for an astronaut? Again, he's going to walk you through it slowly. What's the conclusion of this statement? So of this statement, what's the conclusion? Well, the if is the hypothesis. So you are not more than 6 feet tall must be the conclusion. Write the converse, interchange. Is the converse true? Read what you wrote for number 6 and determine whether you think it's true. Does it have the same meaning as the original statement? So ask yourself, is that a good definition? Here's the third one. You cannot comprehend geometry if you do not know how to reason deductively. Be careful here now. You notice they've got this if partway through. So he's looking for the hypothesis, and he wants the converse. And then you should, well, what's the conclusion of the converse? Now, compare those. Compare the original and the converse. Think about it. Would that be a good definition? You have to determine, is the original and the converse, are they logically equivalent? Here's a mouthful. A true definition. Ooh, right away, a true definition. When you see that, think about what's a definition. Think back to that slide. If the original statement and its converse are both logically equivalent, then that's a definition. So if it's a definition, both those statements mean the same thing. Here's our mouthful. I messed it up. Arachibutyrophobia. You have that if and only if you have the fear of peanut butter sticking to the roof of your mouth. Is that you? Do you have that disorder? Well, what does the abbreviation IFF stand for? A little review. From this definition, what can you conclude about the word arachibutyrophobia and the words the fear of peanut butter sticking to your roof of your mouth? Notice he grabbed the hypothesis and its conclusion. From this definition, what can you conclude about those two parts? If we represented it this way, A implies B, and A is the arachibutyrophobia, what does this part of that statement mean? What does it represent? What does the B represent? Write it out. In words, A implies B for this definition is, back to that other definition, if you have arachibutyrophobia, then you are afraid of peanut butter sticking to the roof of your mouth. Right in words, B implies A. So there's definitely an interchange going here. So we're looking for the converse of that definition. And then, is that sentence necessarily true? Explain. Think about it carefully. Remember what they said at the beginning, and they said it here a couple times. Definition. For a definition to be understood, it's necessary to know the meanings of the words used in it. The following definition of vulgar fraction is correct, but not necessarily helpful. Well, why not? A vulgar fraction is a common fraction that is either proper or improper. Why do you find that difficult to evaluate? Well, which words might not be understood very well? This answer is going to vary for you, for each of you. Write that definition, however, in if-then form. And then write its converse. And then you have to decide, is the converse necessarily true? Why or why not? Again, look back at the direction paragraph up here. That'll help you. When we write a definition, we try to say no more than is necessary. So here's a possible definition of New Year's Day. New Year's Day is a holiday that is the first day of the year. Good definition or not? Well, what if we pare it down? New Year's Day is a holiday. We shortened it up pretty well. Why wouldn't that be a good definition of New Year's Day? It's taking you into that definition of a definition. What makes a statement the definition? Suppose instead they wrote New Year's Day is the first day of the year. Would that version be a good definition? And explain that. Hopefully you're pausing in between these because I'm just running from one to the next. Compare the following two sentences. If it is your birthday, then you get some presents. Only if it is your birthday do you get some presents. This is probably the most confusing set of problems coming up here in the whole chapter, at least for me. Is the first sentence true for you? Is it true that if it is your birthday, then you get some presents? Well, hopefully that's true for everybody. Is the second sentence true for you? Only if it is your birthday, do you get some presents? Only if it is your birthday do you get some presents. It seems to be not true. I have to try to think about that. Is that the only time you get presents? Do they say the same thing? I don't think so. So which one of those two fits this picture? Is it if it is your birthday, then you get some presents? Is there just a single unique place where the X can fall for that sentence in that diagram? How about this? Only if it is your birthday do you get some presents. I think it's 2 in this one, because the only way that you can get some presents is if it is your birthday. So only if it's in the birthday circle do you get some presents. So I'm saying the second sentence fits this picture. First one doesn't. If it is your birthday, then you get some presents. Well, I could be right here and get some presents. Oops, right there and get some presents. I could be right here and I'm not getting any presents. I'm outside of that circle. Another one, someone along the same line. Compare the two sentences, both of which are true. Both of which are true. If it is dry ice, then it is frozen carbon dioxide. If it is dry ice, then it is frozen carbon dioxide. Only if it is dry ice is it frozen carbon dioxide. These are both true. Does it fit this diagram up here? If it is dry ice, it is frozen carbon dioxide. Only if it is dry ice is it frozen carbon dioxide. Now I could have an X right here, and it would be frozen carbon dioxide without being dry ice. Well, no question yet. What relation does the second sentence have to the first? Appears to be the converse, doesn't it? Draw an Euler diagram to illustrate the second sentence. So use this spot. What would the second one be? Only if it is dry ice is it frozen carbon dioxide. Only if it's in the dry ice circle can it be frozen carbon dioxide. So that's the diagram we're looking for. Combine the two into a single sentence by using the words if and only if. Combine these two. If and only if. This one's just some fun here. It is a whodunit if and only if it is a detective story. That looks like a good definition because I see that IIFF in there. And if it's a detective story, it's a whodunit. That's the point of them. Suppose the teacher crossed out the second F with a red pencil. What kind of mistake did she think you made? Or he? To which of these sentences would the corrected statement be equivalent? So if she crossed this out, the corrected statement would say, it is a whodunit if it is a detective story. So you need to pick one of these two. Which one would it fit? Which one would that fit? Would it be safe to conclude that your English teacher's knowledge of math is iffy? Clever. So we have a statement here. Probably a pretty good definition. A car is a convertible. Well, we know it is because here we see that if IFF, if and only if. A car is a convertible if and only if it has a removable top. Well, we've been saying all day that definitions are made up of two conditional statements, the original and its converse. Now he wants you to write the two conditional statements that are equivalent to that statement. So think about it. Two conditional statements. If this, then that. If this, then that. Think back to the very beginning of this lesson. What relation does the second of your statements have to the first? Hopefully you got the point of definition. Set 3 is really fun. It's challenging. Not very many people get it. It's a puzzle in logic reasoning. The Wason test, after Peter Wason. 4 cards are on the table. There they are. Each card is red or blue on one side. You see a red and a blue. So you know on the other side it's not red or blue, because it's red or blue on one side. These 2 cards over here, one's red. I mean, it could be red or blue, could be red or blue on the other side. The other side has a triangle or a circle. So we know on the other side of this is a triangle or a circle. The other side of that is a triangle or a circle. The only possibilities. The following conditional statement supposedly describes the way that the cards are made. If a card is blue on one side, it has a circle on the other. That describes all the cards in this deck. The puzzle is to figure out which cards have to be turned over to find out if this statement is true. Turns out that the obvious answer chosen by most people is wrong. Which cards would you choose, and explain your reasoning? So think it through. If you want some help, maybe I've got some slides here that follow. I'll just kind of zip through them. Remember, this is the statement we're after. This is what we know is true. If a card is blue on one side, it has a circle on the other side. So try to figure out which cards you'd choose. So circle, circle, triangle, triangle, circle, blue, circle. Yeah, you can play that back if you want, see if that helps you, but which cards, notice the question again, where did it go? There it is. Which cards would you choose? I think the idea is get as few as you can. I mean, if you turned them all over, you'd know for sure, but that's not necessary. All right, work these all through. See if you have any questions for class tomorrow. And I will see you there. Got to get to the end.